Warning, the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a continuation of a video series on angle measure for pre-calculus, and this, unlike many other videos for trigonometry review and pre-calculus, should not be a review. This should be totally new. Now, if you took trigonometry, a full course in trigonometry, outside of the Los Rios Community College District, you might actually have had this topic in your trig course. I would prefer to have taught this in a trig course, to be honest with you. It's a really nice topic, and it's good while you're learning trig to see this topic, but it's just not in our curriculum. We don't do it in trig, we save it until pre-cal. So anyhow, let's talk about circular motion, specifically linear and angular speeds. So this is the definition of linear and angular speeds. Suppose a point moves along a circle of radius r, and the ray from the center of the circle to the point traverses theta radians in time t. Now I'm going to pause my reading there so that I can showcase what this looks like. So we have a circle, and let's pretend the circle has radius r. And now we are going to say that we have some type of object or a point that moves along the circle, or along the circumference, if you will, and it cuts out an angle in radians. I know this only displays degrees, but let's just suppose it's cutting out a certain angle in radians. Let's get beyond that. Let's get to about there. And let's say that took me 5 seconds to move from the rightmost point to the leftmost point. Then we define the linear speed to be the distance you covered divided by the time it took you to cover that distance. That should make total sense, because that's how we define speed in the real world, is distance over time. So this is the length of the arc right here, arc length, over the amount of time it takes to go that distance. So that should make sense. Distance over time, miles per hour or inches per second or something like that. So that would be the, by the way, this is the arc length and this is the radius of that circle. So anyhow, that's a logical way to define speed, is just distance over time. Now, at the same time that we can define linear speed like that, just how quickly are we moving along the edge of the circle, we can also define how quickly that angle is opening. Oops, I couldn't see what I was drawing, so I drew it kind of awkwardly. There we go. So we need to actually, or it would be nice to also discuss how quickly does that angle open. It opened from here going in that direction, that's fine, but it took us 5 seconds, let's just say, to open that angle. So just like you can define a linear speed to be the linear distance divided by time, you can define angular speed to be the angle measure divided by time. So it's just basically a distance over time again. Something I want to draw your attention to, because this tends to throw people off a little bit. So I'm going to go ahead and draw yet another circle here. Let me give myself a center, because often it's difficult if I don't start with a center. So let's go ahead and just get a circle drawn out there very quickly. And we are going to open up an angle here. Now, let's pretend, actually, let's put 2 circles on here. Now that I'm thinking about it, let's put another circle, and we'll put this circle to be a little bit smaller, in fact, quite a bit smaller. And I'll make the smaller circle red. How's that? All right. Now, if you were to have a ray going out from the center of this these circles to their edges. And we had another ray going from the center to the edges, just like I have there. You would have to agree that the angle that got cut out here is the same in both cases. It's the same angle that gets cut out in, let's just say it took a second to open up that angle. That angle is the same. The angular speed is the same no matter what. That is, it opened up that many radians in 1 second, whether the circle was the blue circle or the red circle. However, the distance that got cut out, the linear distance that got cut out in that time, is totally different. This is S sub blue, and this is S sub red. Those two distances that got cut out by this angle, this distance here versus this distance right here, are completely different. The blue distance obviously is larger. And so note that the linear speed, if the edge, or I'm sorry, if we start at the initial side here, and we open to this terminal side here in 1 second, the blue, whoever's running along this blue track, has to run a lot faster than the person running along the red track. The angular speed is the same in both cases. So this is just an aside for me to note here. So angular speed, I'll say, does not depend on the radius of the circle, but linear speed does. That's sort of mathematically untrue, but I'm going to say it that way just because if you open through an angle of, let's pretend, 7 pi over 6 radians, and you do that in a 10-second period, well, the linear speed for somebody to keep up with that opening, their linear speed has to increase if you increase the size of the circle. But the angular speed does not care about the size of the circle. All it cares about is how quickly that angle is opening. Now, I did kind of hem-haw about this. Like, when I say angular speed does not depend on the radius of the circle, that's sort of a lie, because angles are related to radius in all of mathematics via this formula, S equals R theta. So technically, you could solve that formula for theta, and you would get that theta in radians is arc length over radius. So technically speaking, it is true that theta does depend upon the radius, but not in the conceptual concept, or in the conceptual frame, which is that we are really looking at, as this angle opens, if it opens to a certain radian measure in a certain amount of time, that's constant. But the linear speed for something along the edge of the circle, well, that changes if you increase the size of the circle. Let's step away from that, and let's also, every single page here, write down those two formulas, just so we start getting in the habit of remembering those formulas. So the linear velocity is just how far we've gone along the arc per unit time. And the angular velocity, which, by the way, I didn't say that, but that is not a W, that's an omega. It's just traditional to use the omega for angular velocity, is just how many radians you go through in a certain amount of time. So angle per unit time, or radians per unit time. And that is actually an important point. I should point an arrow at that and just say that theta is in radians. Again, all of mathematics from this point forward is pretty much works well with radians. It falls apart when you work in degrees. So you have to do some conversion there. And speaking of conversion, this theorem just gives us a conversion between linear speed and angular speed. So linear speed is equal to the radius of the circle times angular speed. And the proof of this is actually pretty easy. If you take the linear speed, which is V, oops, let me get the right color in here, and we want to end up with R times omega. Well, linear speed is S over T. And if you want to get omega in there, you need to actually include an angle. But luckily we happen to know that arc length is radius times angle in radians. And that would be radius times theta over t. But theta over t, off to the right there, is omega. There you go. That's just r omega. And so again, when we go to our next page, we are just going to write down this conversion factor. V is equal to r omega. And actually, I'll even write this one down. S is equal to r theta. These four formulas pretty much are glued together in trigonometry, and that's it. There's no other ones that we have to worry about when it comes to linear speed and angular speed. So those are the four we're going to continually reference. The bottommost one is the one we're very, very familiar with. That arc length is radius times the angle measure in radians. And then the top one is actually the second most common that we're used to, because it is just saying velocity is distance over time. And then the next one is somewhat easy to grasp, because it's just angular velocities, the amount of angles you go through per unit time. And finally, the last one is more memorizable. It's just a relationship between linear velocity and angular velocity. And now that I said that, I do want to go ahead and point an arrow at that and just make sure you know that that is linear velocity. Velocity along the edge of the circle. And this is angular velocity. Velocity of the angle. How quickly is it opening? And I'll use velocity and speed hand in hand, although technically they are two different things. Velocities can be negative and speeds cannot be, but these are technically velocities. I just say speed every once in a while. I think the author of the textbook that I use calls it speed, even though it should be velocity. So let's go ahead and find the linear velocity given that. So this is just a standard plug and chug example to get us started. We're going to find the linear velocity given that S is 5,000 miles and T is 100 hours. This is something that a pre-algebra student can do, right? Because it's just miles per hour. So linear velocity, remember, is distance over time. Pretty easy, right? And distance in this case is 5,000 miles. And time is 100 hours. So this, I don't know what I was writing there, but this should not be a brain teaser for you. This is just 50 miles per hour. And that's it. So this is nothing major. This is just kind of showcasing that, honestly, linear velocity is just like what we're used to forever. We know how to compute speeds, distance over time. That should not be a hard part to these problems. But then we graduate up a little bit, and just before we begin, let me go ahead and write out all the formulas we have. I'll start with S equals r theta. Arc length is equal to radius times angles, and the angle is in radians. Linear velocity is distance over time. Angular velocity is angles over time. And finally, the relationship between linear velocity and angular velocity is V equals RW. Those are the four formulas. All right, let's take a look at this problem. A piece of gum is stuck on the bottom of your bike tire. You've been traveling 10 feet per second for the past 4 minutes. What is the linear distance the gum has traveled? So this is actually incorporating our new formulas here, believe it or not. We have a bike tire, and on that tire, a piece of gum got stuck at some point. And then we kept riding. We didn't know. And so then as we move forward, the bike or the gum just keeps going around and around and around. And we want to measure if we had unwound this. You can think of this as a string going around and around and around. And by the time we stop, let's just say we stop there. By the time we stop, you want to be able to straighten out that string to figure out how long is that string? How far have you carried that string with you, essentially? So you've been traveling 10 feet per second for the past 4 minutes. What is the linear distance the gum has traveled? Okay, well, let's look at all these formulas. They gave us that we've been traveling 10 feet per second. That is our linear velocity. So this statement right here is telling us that our linear velocity is 10 in its feet per 1 second. It's going to be important. Units are incredibly important here. And this is an amount of time past 4 minutes. So I'm just going to go ahead and highlight this part right here. And I'll just say that this is t equals 4, but that's in minutes. So we're going to have to do some type of conversion here. And I probably would convert to seconds since our unit for linear velocity is in seconds. I just want to convert this to seconds. So that would be 60 times 4, or 240 seconds is how long we've been traveling. All right. Now look for a formula that involves both linear velocity and time. And it's this second formula right here. Notice what they're asking is, what is the linear distance? So we want, the linear distance is a distance. It's an arc length, essentially. We want s. And so, not s factorial, but just s. So what we want to do is solve this formula right here for s. We're going to multiply both sides by t. Let me grab that formula and I'll move it out here, and I'll just say then that implies vt is equal to s. This is not a second formula you have to memorize, because you can always derive it just from this. So don't bother memorizing it. Memorize the v is equal to s over t. So we want s, and look what we have. We have v and t ready to be used. So let's go ahead and plug in v, which is 10 feet per second, and t, which is 240 seconds. So s is going to equal v, which is 10 feet per 1 second, times t, which was 240 seconds. Oops, that's not how to spell seconds. And notice the units for seconds cancel beautifully. And so you get 2,400 feet. And this is how far that piece of gum has basically traveled, is 2,400 feet. That's also how far you've traveled with the gum on your tire. So this is a good example of the fact that when you're working with these problems, you're going to be referencing those 4 equations over and over again, those 4 formulas off to the right-hand side. And it is critical that you really get used to these formulas, because they end up becoming dominant in these problems. Let's switch gears a little bit. So let me go ahead and go off the side. And if you're wondering, I do have big examples in a little bit. I'm sure you're not wondering, but I'm just going to tell you. And so we're just building our way up to those. So this is arc length is r theta. Linear velocity is distance traveled over time. Angular velocity is angles rotated through per time, and then the relationship between them. Linear velocity is radius times angular velocity. Find the angular velocity given that we've rotated through an angle of 135 degrees and it took 4 hours to do that. Notice how I said that. We've rotated through an angle of 135 degrees and it took 4 hours to do that. So let me rotate through an angle of 135 degrees, and we'll remove that from the screen. And note it took 4 hours to do that. All right, and I didn't bother pinning there, so let me just do this. So this is a 135 degree angle, and we want to find the angular velocity. Notice the angular velocity, which is omega right here, doesn't really care about how big the circle is. And so I didn't tell you the radius of the circle. And that's what I had mentioned earlier, is that angular velocity does not rely upon the radius of the circle. It doesn't really matter. What matters is how quickly are you opening the angle. Another thing you need to note for all of these is that theta will always be and must always be in radians. And so both of those thetas there have to be in radians. So we must convert 135 degrees over to radians. And luckily we know what that is. That's 3 pi over 4 radians. So I'm just going to write that in down below. You should be very familiar with that from your trig course. That you should know from your trig course. So, all right. So 3 pi over 4 radians. So our angular velocity is going to be radians per time, which is 3 pi over 4 radians per 4 hours. And that will be, and I should write hours down here. And that will turn out to be 3 pi over 16 not times, but the units of that would be radians per hour. Now, radians are a unitless measure, but when you're using them in a rate like this, it's probably best that you mention them. So the numerator was in radians and the denominator was in hours. It's just better to say, oh, this circle opened up at 3 pi radians per 16 hours, or 3 pi over 16 radians per hour. Either is the same. They're both the same. But if you just say this angle opened at 3 pi over 16 per hour, that sounds weird. So it's best to include the word radians, even though radians is unitless. It's important here to probably include them so people know what you're talking about. Now we get to more entertaining examples. So a mixing blade on a food processor extends out 3 inches from its center. So even before I continue, I'm going to go ahead and just draw out a picture of this. So we have some food processor with a central blade or something that spins around in circles. And the blade itself is 3 inches in radius. So that is slightly off center. I'm going to have to plot it right there. So we have a 3-inch radius blade. 3-inch. Okay. If the blade is turning at 600 revolutions per minute, what is the linear velocity of the blade's tip in feet per minute? So there's a lot of things going on in this problem. First of all, 600 revolutions per minute. That is sort of, not exactly, but sort of an angular velocity. Remember, I should have written this down, but all of our formulas are, let's see, arc length is radius times theta. Linear velocity is just distance over unit time. Angular velocity is angles per unit time. And finally, the relationship between linear velocity and angular velocity. If you look at the angular velocity, it's not revolutions per time. It is angles per time. Again, I'm looking at this right here. It's angles in radians per time. And we have revolutions per time. So this, we're going to have to do a little bit of conversion. Our angular velocity is theta per time. Well, we did 600 revolutions per 1 minute. But that's not an angle, is it? Revolutions is not an angle. I need to get to radians. So I need to do some unit analysis. I need to take out the word revolution and introduce the word radians. Well, what is how many revolutions do you have, or how many radians do you have per revolution? Well, we have 2 pi radians for every 1 revolution. This is actually the number 1, by the way. If I told you, oh, I have an angle of 2 pi radians, and somebody else says, oh, that sucks because I have just 1 revolution of a circle, you would say, oh, you two have the same thing. These are the same pictures. They mean the same exact statement, that you've gone through a full rotation. So because the numerator is the same as the denominator, you're essentially multiplying this fraction by the number 1. So you're not really changing it other than the look. So I'm doing a unit analysis or a unit conversion from revolutions to radians. You see the words revolutions cancel beautifully. And this turns into 1200 pi radians per minute. 1200 pi radians per minute, per 1 minute. All right, so let's see. What else do we have? What is the linear velocity of the blade's tip in feet per minute? So I want to use this formula if I can, or let's see, do we have another formula that involves linear velocity? Yeah, we sure do. So which of those two are you going to use? Well, let's see. We want linear velocity. We were given angular velocity and the radius, which is 3 inches. If we're given angular velocity and radius, then this is going to be the winner as far as formulas go. Because if you want velocity, it is equal to radius times angular velocity. So let's go ahead and use that formula. Notice how I did that, by the way. I often, especially in calculus, I write down givens that gave us these two things, and I write down what we want. And then you start searching through formulas or using logic to derive a formula so that you can relate all this information together. Let's see, we have velocity is equal to radius times angular velocity. Well, the radius is 3 inches. So let me write that in here, 3 inches. And the angular velocity is 1200 pi radians per minute. So let me just write that in here, times 1200 pi radians per minute. And before I continue, I'm just going to note that we want the linear velocity in the end to be in feet per minute, not inches per minute. So I'm going to go ahead right now and transform this unit of distance here into feet by using some unit analysis. I'm going to multiply this fraction by the number 1. I'm going to say it's 1 foot, or 1 feet, I suppose, per 12 inches. That is the number 1. Yet it allows us to cancel the word inches. And now we're going to be in feet per minute. Remember, radians is unitless. We would only write that word radians there if and only if we had a rate that was angles per time. Then you definitely want to say, well, that's 1200 pi radians per minute rather than 1200 pi per minute. But when you are using other unit analysis, transforming it, because it's technically unitless, you can remove that word radians. And so you'll see that we end up in feet per minute. All right, so let's do the multiplication here. 12 goes into 1200 100 times, and 3 times 100 is 300. So we have 300 pi, and that's feet per minute. And then you can totally grab a calculator if you want to and type in 300 pi just to get a really good estimate of this. So the speed of the tip of that food processor is 942.5, we'll round to the nearest decimal place, feet per minute. That's approximation, but that's okay. So very fast, 942 feet per minute. You can convert to miles per hour if you want to, but we're just going to answer the question as written. For our next problem, we're going to look at a word problem here. The London Eye is a Ferris wheel on the south bank of the River Thames in the borough of Lambeth. It was the world's largest Ferris wheel from 1999 until 2006, when it was surpassed by the Star of Nanchang in Nanchang, China. The diameter of the London Eye is 394 feet, and passengers enter into the wheel's capsules at an elevation of 30 feet from the street level. The eye makes one full revolution every 30 minutes. I'm going to highlight that piece right there. It makes one full revolution every 30 minutes. That's going to be very important to us. And then, how fast is a passenger of the London Eye moving? One of the things that is going to be somewhat confusing in a real world problem is the amount of extraneous information that they hand us that we don't actually need. For example, if I want to know how quickly somebody is going around this Ferris wheel, I don't really care what height the Ferris wheel is originally at. All I really care about is what is the radius of the Ferris wheel. And that's something that I'm going to go ahead and write down right now. They gave us that the diameter of our Ferris wheel here is 394 feet. And that's going to be something that we have to go ahead and cut in half because we're going to be needing the radius. So I'll go ahead and draw that in. And I went ahead and used red there. So red for radius. And if 394 is the diameter, then the radius is just half that. So what is that? 200 minus, let's see, 3. So 197. And remember, the units that we're dealing in here is our feet. So I just fill that in. Now let's talk about other information that we know. Let's go ahead and actually start by writing down the formulas that are going to be critical for our success here. The 4 formulas that we know: arc length equals radius times angle, where that angle is in radians. Linear velocity is just arc length over time. Angular velocity is just going to be the number of angles in radians over time. And then we need a way to relate linear velocity to angular velocity, and that would be through our final formula. Linear velocity is the same as radius times omega, which is the angular velocity. Let's see what we were given here and what we want. Let's see, we were given, I'll go ahead and write our givens off the side. Let me read through, and maybe I'll erase my highlighter so that we can really just highlight only what we need, right? So let's see, London Eye is a Ferris wheel, blah, 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 blah. The diameter. Diameter is 394 feet, which gives us the radius. We already wrote that down, but I'm going to go ahead and write our givens over here. And there we have our given is, our radius is 197 feet. Let's see what else we have that's important. If you read forward, passengers enter into the wheel's capsules at an elevation of 30 feet. Again, the height at which I enter into this Ferris wheel does not tell me anything about how quickly I'm moving around the Ferris wheel. So that's extraneous information. I actually use this problem for many other problems. And so it's nice to have all this information here for other problems in the future. But for right now, we're just asked how quickly is the passenger moving around the circle. The other piece of information we have here is the eye makes 1 full revolution every 30 minutes. So that's going to give us an angular velocity. You might not think it does, but remember, if you know that 1 full revolution is 2 pi radians, then you know you go through 2 pi radians every 30 minutes. So our angular velocity would be 2 pi radians per 30 minutes. Obviously, you can simplify that if you wanted to. That's just pi over 15. Again, it's still radians per minute. Now, just in case, let's go ahead and look to see if they handed us anything else. No. If you look, now they're just asking how fast is a passenger of the London Eye moving? And just because I want to, I'm going to go ahead and highlight that in blue. That's the stuff we want. We want the linear velocity. So if a passenger was on the London Eye right here, and they just moved along the edge, we want to know how quickly are they moving along the edge of the London Eye. And remember, we have a relationship between linear velocity, what we want, and these two items right here, the radius and the angular velocity. That relationship is given by this formula right there. So we have everything we need in this problem. Let's go ahead and insert all that information in. Linear velocity is radius times angular velocity, the radius being 197 feet, and the angular velocity being pi over 15. And by the way, that's radians per minute. Radians is a unitless measure, so I don't need to actually include the units for the radians in the numerator. And when you glue these together, you get 197 pi over 15, and that is now in feet per minute. That's how quickly a person on the edge of the London Eye is moving. This would be called exact form because, well, you haven't grabbed a calculator. You've reduced this down, but you have not grabbed a calculator. Now I'm going to go ahead and approximate this by grabbing a calculator. And this just basically means once we grab our calculator, you can double check my work here at 41.3 feet per minute. And now we get to what I can consider to be the ultimate problem. Again, before I read this, I'm going to write all the formulas that we will need off to the side here. So we will use s equals r theta. We'll need the fact that the linear velocity is distance over time. Angular velocity is angles over time. And then the relationship between linear velocity and angular velocity is given by v. It's equal to r omega. I will also have to describe to you all the pieces of what's going on in this problem, because there's a lot of interesting information here that often is not that often people don't know about. So I'm going to read this first, and then I'm going to describe it to you. So a professional cyclist is equipped with a 150 millimeter diameter chain ring and a 95 millimeter diameter sprocket. If she was pedaling at 90 revolutions per minute, find her speed in kilometers per hour. Now, I spent a moment or three going through and doing this problem off to the side as far as building it. And we have to assume one other thing here that I didn't write in, which is that we're going to assume the wheel that this is all attached to is 700 millimeters in diameter. All right, so let's go ahead and look at the situation. What do I mean by chain ring and sprocket and wheel? So this is the rear tire of a bike. So this is the rear wheel right here of a bike for a professional cyclist. This, which is attached to the rear wheel, the center of the rear wheel, is called the sprocket. So I'll write that in there. And then we have the chain in red. So that's the chain that connects to the pedal. And the pedal is connected to what's called the chain ring. So this is the chain ring, one word. All right, so let's go ahead now. I hope that makes sense. There's obviously a front tire that does not mechanically make much of a difference for this situation. So let's go ahead and just write in all the information it's given us. A professional cyclist is equipped with a 150 millimeter diameter chain ring. If that's the diameter, then the radius of this chain ring, which I'll just draw right here, is 75 millimeters. It's the 75 millimeter radius. Now let's see what else they gave us. Zooming out so I can see. Let's see. 95 millimeter diameter sprocket. So the smaller piece here, the sprocket, is 95 millimeters in diameter, which is 47.5 radius. So that's a 47. I'm just going to kind of hop out of there and just say 47.5 millimeter radius. Because, is that right? Yes. That'll be a 95 when you double that up. Let's see what else we're given. She was pedaling at 95 revolutions per minute. So I'm going to write that up here as a given. We were given, let me write this in here, given that she was pedaling at 90, was it 95? 90 revolutions per minute. So that means her angular velocity is going to be something with 90 revolutions per minute. Now, before I start writing that in, I want to mention there are 1, 2, 3 circles here. So we're going to have to actually label 3 different pieces of information. And in fact, I'll start by just saying we're given the radius of the chain ring was, let's see, 75 millimeters. The radius of the sprocket was given to us to be 47.5 millimeters. And finally, the radius of the wheel I wrote in at the end is, it has a diameter of 700 millimeters. So the radius is 350 millimeters. And then we were also given that the angular velocity, how quickly the angles are moving for the chain ring, because that's what the pedal is attached to. It's attached to this chain ring. And this cyclist is spinning that chain ring around at an angular velocity of 90 revolutions. Let me just double check that, per minute. 90 revolutions per minute. 90 revolutions per minute. However, we know that each revolution is the same thing as 2 pi, going to write the word radians immediately. 2 pi radians. And so we can cancel the word revolutions. And now we know how many radians per minute she's spinning that chain ring. I hope that all makes sense. So let's see, that's 180 pi radians per minute. That's how quickly she is spinning that chain ring. That's the stuff that we were given. Let's see if there's anything else that we're given. I should probably go ahead and write the radius of this wheel here, 350 millimeters. Why not? Honestly, they didn't explicitly hand us anything else. I'm going to write what I want over here. We want how quickly, find her speed in kilometers per hour. So basically, we want her linear speed. We want the linear speed in the end. I'll say V. But there are 3 linear speeds here. There's the linear speed of the chain ring. How quickly is a point on the chain ring spinning around? There is the linear speed of the sprocket. How quickly is a point on the sprocket spinning around? And that's not in angles. That's in linear, in like, what are we in? Feet or something like that? I think we're in feet. Millimeters, sorry. We're in millimeters. So that'd be in millimeters per minute. And then we have a third circle, and this third circle will give us how quickly this tire, a point on the tire is moving in terms of millimeters per minute. And that's actually, in fact, I think the tire would be going this way. But that is actually what we're interested in. It's the linear velocity of the tire, because that translates to the ground, and that translates to how quickly the bike is moving. So we want the linear velocity of the wheel, is what I'll call that. Let's call that sub t, actually, because W looks like it's used for something else. Even though it's an omega, it looks like it's used for something else. Oh, shoot. I already used W, so let's go ahead and use W. All right, so V sub W. All right. Well, let's start with what she's interacting with. She's pedaling this chain ring, and we already know how quickly that chain ring is moving in angles per minute, right? We computed that out to be, where is it? Up here. 180 pi radians per minute. That's the angular velocity. So I'm going to just write that here. Just doesn't hurt, right? The angular velocity of the chain ring is 180 pi radians per minute. Okay. And we have a radius, which means that we can find the linear velocity of this point. And the linear velocity of that point, think about it this way. If that point was instead right here, it would move at that speed all the way around here and all the way back here and translate over to this. It's not moving any faster when it gets to the sprocket, actually. So the fact that it's the same point, let me say that again. This point right here, it goes to here, to here, to here. It just gets carried along. It's a link on this chain, essentially. It gets carried along. It's moving the same speed. Let's say it's moving, I don't care. Let's say it's moving 50 millimeters per second or something like that. By the time it gets here, it's still only going to be moving 50 millimeters per second. And then it rushes back around. So the linear velocity of that point along the chain ring will be the same as the linear velocity of that point when it gets to the sprocket. That's critically important for this problem. So let's talk about the linear velocity of that point on the chain ring. Well, the linear velocity of that point is going to be the radius of the chain ring times the angular speed of the chain ring. And we have that information. By the way, the formula we're using is this one right here. And we have that information off to the right. It's our given information. So I can trade out radius of the chain ring for 75 and the angular velocity of the chain ring for 180 pi radians per minute. I'll go ahead and do that. So this tells us the linear velocity of the chain ring is, like I said, 75 millimeters is the radius. And the angular velocity, so wrote off to the side there's 180 pi radians per minute, which is just 180 pi per minute. So this tells us how quickly a link is moving along this chain. Not bad, right? But that's not what we want. I'm going to keep these numbers as written. So this point that was right here and got moved along the edge and is moving at that number, we'll just call that v sub c. It's moving at a speed of v sub c. It gets all the way up here, all the way over here. It's moving at a speed of v sub c. It's moving at a speed of v sub c. It's moving at a speed of v sub c. It still is moving at a speed of v sub c. So v sub c, is going to be the same thing as v sub s. So we need to go ahead and find out how quickly is this angle changing here, so that we can translate that over to the edge of the tire. And the way we do that is, since v sub c is equal to v sub s, and we know we have a formula for to relate the angular momentum to the radius, we could say, oh, v sub c, which is equal to v sub s, must equal the radius of that sprocket times the angular velocity of that sprocket. Now remember, we have just computed v sub c, so therefore we know v sub s, and we were handed the radius of the sprocket. So therefore we can find this missing angular speed. And once you find the angular speed of the sprocket, you then can tell me how quickly that tire is moving, and that would be how fast the person's biking. So let's go ahead and do this. V sub c, which is v sub s, is equal to, I think we said 75 times 180 pi millimeters per minute. Let's double check that actually. Yes, 75, it's this I'm looking at right here. 75 times 180 pi millimeters per minute is what that is. And that is supposed to equal the radius of the sprocket, which is 47.5 millimeters, times the angular velocity of the sprocket. And we don't know the angular velocity. Let's go ahead and divide both sides by 47.5 millimeters. This ends up being 75 times 180 pi millimeters. I'm about to erase that though. Divided by 47.5 millimeters and then times minutes. But we know that, and by the way, that's the angular velocity of the sprocket. But we could see that the words millimeters are going to cancel beautifully. And so this gives us a unitless measure on the top, which is a radian, divided by minutes. So this is number of radians per minute. This works out beautifully. So now we have the angular speed of the sprocket. Now I need to go ahead and move to the big old tire here. I would love to know what is the linear velocity of that wheel. That's what we want. Let me write that a little bit larger, v sub wheel. There we go. That's what we want. Well, we know that this wheel, which is just moving this point along the edge really quickly, that point, how quickly it moves, is based upon the angular velocity via this formula right here. Velocity of the wheel is equal to radius of the wheel times the angular velocity. These are actually W's, so maybe I should do it like that. Wheel, and then the angular velocity of the wheel. Well, we have the radius of the wheel. The radius of the wheel is 350 millimeters. It's equal to 350 millimeters. And technically, we actually have the angular velocity of the wheel because we found the angular velocity of the sprocket. And remember, angular velocities don't care about what size circle you're dealing with. So if this angle rotates, let's say we go through a full rotation here in a second. Well, then this tire goes through a full rotation in a second. It's the same angular velocity. So the angular velocity of the sprocket is going to be the same thing as the angular velocity of the wheel. And so that's what we're going to replace here. The angular velocity of the wheel is therefore 75 times 180 pi, and that's in radians, over 47.5, and this is in minutes. And notice what we have, millimeters per minute. And that's how quickly, whatever this number is, this is how quickly the tire is spinning linearly, like how fast the tire is moving along the ground. But it is not listed in kilometers per hour or anything like that. This is listed in millimeters per minute. And I think, let me zoom out, that we want our answer in kilometers per hour, yes. So let me copy this answer up above. We had 350, 75. Let me just write that here. 350, 75, and 180 pi millimeters. And that's minutes in the denominator. Although the 47.5 didn't come from minutes, it came from something else, but that's okay. It's still, the units are millimeters per minute. If you don't like those units being listed like that right there, you can always write them off to the side as millimeters per minute. And now we have to change into kilometers per hour. Well, that's not too bad. There are 1,000 millimeters in a meter. So let me go ahead and do some unit analysis. And I need some room here, so I'm going to grab this and move this off to the left here. All right. I'm going to go ahead and get out of the millimeters by saying, well, 1 meter is the same thing as 1,000 millimeters. So you can see the words millimeters cancel beautifully. But that gives me meters per minute. I don't want meters per minute. I want kilometers per hour. So let's go ahead and also say, well, 1 kilometer is 1,000 meters. And so the words meters also cancel out beautifully. Let me go ahead and do that. Notice that we are now in kilometers per minute. And so the final conversion will be, I guess I'll just use black ink for this final conversion, is to get out of minutes. So we know there's 60 minutes per 1 hour. And so the words minutes will cancel beautifully. And now we are in kilometers per hour, and we can go ahead. I'll write it out first, and then we'll grab a calculator. But this is 350, 75, 180 pi times 60 divided by 1,000 times 1,000 times 47.5. And 1,000 times 1,000 is 1 million. All right. And this is kilometers per hour. All right, let's grab a calculator and find out what this is. This is approximately 18.8 kilometers per hour. Now, you might not know what that means as far as miles per hour, but 1 kilometer is roughly around 0.62 miles. So if you wanted to convert to miles per hour, you could totally do that. You can just multiply it. They didn't ask us to, by the way, but you could totally say 1 kilometer is the same thing as 0.62 miles. And then you can do that conversion. And that's approximately 11.7 miles per hour. There you go. So there's a really robust, you could totally tell that's a very robust problem. But that's a good pre-cal problem right there. I used to give this problem to my trig students. I probably could still, honestly, if we spent quite a bit of time talking about this style of problem. The main thing to note is that you're transferring linear velocities across to a different circle. That's the main thing, is that you're linking the chain ring to the sprocket via the chain, and the linear velocity of the chain just doesn't change. The linear velocity on the chainring will be the same as the linear velocity on the sprocket. And then the second thing to note is that the angular velocity of the sprocket will match the angular velocity of the wheel. That's how you link those two. So that's how all this problem kind of works out. A really fun problem. I really dig this. I've given this on exams before. So, all right, that's the end of this video. I think we're pretty much done with this new concept. And yeah, I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.